Welcome to the session. Let me introduce the speaker, Piotr Achinger. He's a specialist in algebraic geometry, topology, and homotopy theory of algebraic varieties and rigid analytical spaces. He got a PhD in 2015 in University of California, Berkeley, and then spent 2 years in IMPAN and UHS in Paris. He has many awards, among them, let me mention here, the Kazimierz-Prokofsky Award, which is jointly organized by Polish Mathematical Society and the Institute of Mathematics, Polish Academy of Sciences. He's a holder of the ERC starting grant. We have only 2 of them, and there will be another talk next. So the title of this theme of this ERC grant is Homotopy Theory of Algebraic Varieties and Wide Ramifications. And obviously the short title of this is Capybara. Maybe you can explain that. I was trying, but I failed. So the floor is yours.
Thank you for the introduction, and congratulations to all the laureates of this prize. So far, most of the talks were about differential equations, so I didn't want to be like an outlier. So what I do is it's algebraic geometry, and it might come as a surprise to you that differential equations also are important in the study of algebraic varieties. I found it funny that Marcin Soka had basically the same title as mine. It was equations and geometry. Yeah, right. Okay. So since this is mostly a mixed analytic audience, I will not assume any knowledge of algebraic geometry. What else should I say before? So I will not assume any background. Maybe the last slide, which will be mostly about, I will mention something about my own work, then that will be more technical, but at least it will be very short. So mostly this will be, I will be talking about classical work of Deligne, or even going back to Fuchs in the 19th century. And I wanted to sort of like paint a broad picture for you. Not this picture, I didn't paint this one. So if there's one important thing that you should like have like as a takeaway point from my talk, and then you can stop listening, is the following. I should click on the slides. Right, it's this. So this is an advertisement. Like some people yesterday took the opportunity to advertise an event. I want to advertise this one. So this will be an opening event for the International Center of Mathematics in Ukraine. It's like a kickoff event in the sense that the center will not like start like physically like an operation, but this is like a kickoff event for a big initiative. And we have some prominent speakers. Bergelson, Tao, and Gazowska will give mini courses, and Kołaga, Przymus, Lemańczyk, Malinic, Radczenko, and Rodriguez Vegas will give lectures. So yeah, this is in August. As you can see, very big font, and the website is here. Everybody's invited. And which I didn't explain, but it's on the poster, is that this event will be jointly held here and in Kiev. Actually, all of the speakers except for Marina Gazowska will be physically here. Okay. Okay. Now let me get to the math. So I will be talking about topology of algebraic varieties. So if you don't know what an algebraic variety is, it's like a system of polynomial equations, or the set of solutions of polynomial equations. And today everything will be over the complex numbers. So I have C to the capital N, that's my space. And I have F1 through F1 are polynomials cutting out some set. So That's it. And now the general problem is that I want to understand the topology of that set. So mostly if you heard something about algebraic geometry, people consider what's called the Zariski topology on such a space where only the closed sets are given by some further vanishing sets of polynomials. This is not what I'm talking about. Over the complex numbers, I want the actual like Euclidean topology induced from C to the n. So I want to understand this topological space in some like quantitative way, like as a shape. I said up to homotopy. So this means I want to sort of understand the broadly understood shape of that space. But I want to do it in an algebraic way. I will not explain to you now why this is important to do it in an algebraic way, but an algebraic geometry sees this space and thinks of this ring here, which is the quotient of the ring of polynomials by the ideal generated by these equations. So this is the ring of polynomial functions on the space. And as in the correspondence between a commutative C-star algebra and a compact Hauser space, here we think that space X is the same as this ring R. Okay. So like even like I can simplify this even further and it still will be interesting. So the baby examples throughout the talk will be just the line minus a finite set of points. Okay. So it's an open subset of the line. So, but I said I want to look at this vanishing sets of polynomials. So how is this set a vanishing set of polynomial if it's open? Well, I have to add a new variable, W. Z is the coordinate on the line. W is the coordinate, the new one. And then the equation here says that W is the inverse of this product of Z minus alpha I, which means this is the ring of irrational functions whose poles are in the set of the alpha i's. Okay, so I want to understand these like topological properties of this space using this ring. Here's like a completely basic example. I want to see if the space is connected. The space is, if the space is disconnected, is the joint union of two things which are also algebraic varieties, although it's not completely obvious. And then the ring R is a product of the rings of coordinates on one piece and the other. So X is connected if and only if this ring R is not the product of the ring. So here's a basic property, but it gets more complicated when I want to recover some more refined invariants of my space X. So a natural source of such invariants is algebraic topology. And the corresponding invariants are things like the fundamental group, which is the group of homotopy classes of loops at the space X. I will mostly just, there should be a base point, but I will omit it all the time. And there are some homology, cohomology groups, which measure some kind of holes or shape of the space. And in general, it's impossible. So let me say what is impossible. It is impossible in general to take this ring R and recover from it just algebraically the invariant or the homotopy type of the space X. Okay, so this is an important example you just said, and many. Let's see, this was very long ago, and many examples have been found since of two varieties with the same ring of coordinates, say, so algebraically are the same, but they have different fundamental groups. So I said an example of X and an automorphism of the complex numbers, so that's some a priori horrible thing. Like a discontinuous automorphism of the complex numbers as a field, where when I apply this automorphism to the coefficients of my polynomials, then I get a new variety, which algebraically is the same, but the homotopy type is different. Okay, so the answer is that this is what I wanted to do is impossible. But we can recover some things, for example, whether the space is connected, but we can recover some, I said, shadows of the homotopy type of X. So this means maybe I don't know the fundamental group because it's not uniquely determined by the algebra, but I know something about that group, and I will explain what I know about. Okay, so one example is what's called étale homotopy, developed by Grothendieck and his collaborators in the 60s and 70s. So there is something called the étale fundamental group. I will not explain to you what it is, but it is a pro-finite group, pi1 étale of X. So this is, what's a pro-finite group? It's a closed subgroup of a product of finite groups, okay? An infinite product, so this infinite product is not discrete, and I'm looking at closed subgroups. So it is, it's like has a topology of a Cantor set, more or less. And there's this group, which is defined in algebraic way. It has a flavor of a Galois group, such that for every if I map my fundamental group, this is the thing I want to understand, pi1 of X. And if I look at homomorphism from that group to any finite group G, these two groups, the one I can construct and then the one I want to know, they have the same homomorphism to every finite group. To be more precise, this pi1 étale is what's called the pro-finite completion of pi1 of X. So it somehow depends naturally on the thing I want to understand. So for example, there are two, when you go to the previous slide, see, I had these pi1s which are different, but the next slide tells me that the homomorphism to any finite group from this one and that one is the same. So I know quite a bit about this fundamental group. Okay, so here is an example. If I look at this line without a number of points, then I will give you the algebraic recipe. So this capital K is C of Z, so this is just a field of rational functions. Now I take its algebraic closure K bar, and then look at this intermediate extension K tilde. And I will not explain this fully, but this is an algebraic recipe. This is the maximal subfield, which is unramified away from these points. So I look at extensions, which they are unramified at every point except for these removed points alpha I. And then the Galois group, so the automorphism group of this large field K tilde over K is this étale fundamental group. And this is something that I can understand algebraic. Another thing is étale cohomology. So this is another recipe, not for the pi1, but for the cohomology of the space, where I look at the finite group lambda, which is the group of coefficients. Maybe it's a pro-finite group, or maybe finite. So maybe this is D mod n or ZP. And I can recover the singular cohomology of X with coefficients in lambda. Okay. What I would like to understand, sort of the ultimate thing, would be to recover cohomology with integral coefficients. This the theory doesn't let me do, and in fact, this cohomology ring is not uniquely determined by the space. Okay, so this is like a shadow of some homotopy type in the world of finite groups that I can recover algebraically. Now I'm going to talk about some different shadow, which is a shadow sort of with complex coefficients and not finite coefficients. So one of such is what's called the Rham cohomology. So now I will suppose my X is smooth, which means this X is a manifold, more precisely means that, well, I can just say algebraically that the matrix of the Jacobian matrix, partial derivatives of these equations with respect to the coordinates has at every point a maximal minor which doesn't vanish. Okay. Now something you can remember from some elementary differential geometry or differential topology course is the Rham's theorem. It tells you that the singular cohomology of a manifold can be recovered using differential forms. Namely, I have a differentiable manifold, so a thing appearing much different from an algebraic variety, and I look at the space of order I differential forms. So these are C infinity forms. on my manifold. And then there is this operator of there's differentiation of differential forms. And they form what's called a complex. I can go from I forms to I+1 forms. And if I go twice, I get zero map. So this is what's called the Rham complex. And the cohomology of M with real coefficients is, that's the theorem says, it's the same as the cohomology of that complex. A cohomology of the complex is the kernel of the ith map divided by the image of the previous in the complex. Okay, so this is a recipe. It looks relatively algebraic, but it's kind of useless sometimes because this is a huge space of all different C infinity differential forms. It's not like I can describe that space in a reasonable way. So here comes this theorem of Grothendieck, which is an algebraic counterpart of this Rham's theorem. So we have algebraic differentials, which are sort of like differentials with polynomial coefficients. Here's some algebraic recipe. So it's just like 3 modules spanned by these dxi, where xi are coordinates, and then divided by some submodule dependent on their equations. It's not important what the formula says. And this gives me the possibility of constructing an algebraic version of this Rham complex. Okay, so it's just like, it just says that if I take a differential form of complex values with polynomial coefficients and I differentiate it, and I can get polynomial coefficients, right? And here's this theorem of Grothendieck, which I find extremely surprising. It's a natural theorem to state, and but it's surprising that that it is true. Is that the cohomology of complex coefficients of my space is the cohomology of the algebraic Rham complex. So somehow the polynomial differential forms see the entire sort of topological content in this space. So just let me show you an example for this theorem, and then you will see how it works, and then you will recognize it as something you already know. So here is an example. And we come back to this basic example, just the running example. So X is again the punctured line with some punctures alpha I. So the ring R is take polynomials and add the inverses of Z minus alpha I. So rational functions which only have poles at the alpha I. And then the first homology of this space X is has as a basis loops around these punctures alpha I. I didn't have a picture, maybe I will not draw it, but you can imagine loops going around every puncture. Now, if I look at this, the Rham complex, well, this is, I'm in dimension 1, so I only have 0 differentials, which are just functions, and 1 differentials, which are just functions times dz, okay? So now the interesting invariant is H1, which is the co-kernel of the map. So as I look at all differential forms, some polynomial or rational functions times dz, and I quotient out by those which are the derivatives of some function. Okay, so this is spanned by these forms dz divided by z minus alpha I. So this is something that you can recognize, that you can sort of, if you want to differentiate a form like this, dz minus z minus alpha I, then this should be like log of z minus alpha I, and log is non-algebraic. So this is not in the image of the differential. And then you should combine these two with the Cauchy's formula, which means that the integral of these along the gamma I of this differential form is like a pairing between this basis and that basis gives you 2 pi I. Okay.
It's easier. These forms have residues. And
exactly. Yeah, I just wanted to say that if you want to integrate a function on the plane which has some poles at these alpha I, then the residues at these points are the sort of obstructions for you to integrate. And so, so this pairing is given by residue. Okay, so here is I wrote the name periods for this slide because this is explanation for this number 2 pi I appearing here. And so the Rham cohomology gives us some interesting numbers, which are called periods. So here's the recipe. And here we get some interesting gadgets from linear algebra. So sometimes in algebraic geometry, you get some interesting linear algebra things. So x is, suppose now that x is defined by polynomials with rational coefficients. So I'm sort of one leg in number theory now, right? And so my ring R is some ring RQ, which is the same ring like this quotient ring, but with rational polynomials, and then tensored with complex numbers. And then I can look at the cohomology with rational coefficients of my space X, okay? That is a rational vector space. And now I can also look at the cohomology of this algebraic de Rham complex, so algebraic de Rham cohomology, but with rational coefficients. It's another rational vector space of the same dimension. I have two rational vector spaces of the same dimension. So first they are isomorphic, but the natural isomorphism that comes from natural identification, which comes from Grothendieck's theorem, is an isomorphism only after I tensor both of them with the complex number. So if I pick a rational basis of V and W and express this isomorphism, I get some interesting array of numbers, which are typically not rational numbers. And these numbers are called periods. So for example, here, we saw that 2 pi I is a period for this variety X. And so we saw that phi is a period. And there are interesting number theory conjectures, for example, that E is not a period. We have no idea how to show that, okay? Now, we come finally to differential equations. So I explained some things about cohomology. Now I will be talking about fundamental. So now the point is that differential equations give me a window to looking at some part of the shadow of this fundamental group that I want to understand. In the same way that in which I already mentioned Galois theory gives me another window when I can see representations of my fundamental group in over finite rings. Here I look at representations of the fundamental group, complex representations, okay? So the idea is to look at the behavior of solutions of differential equations. And this is again something you recognize from any course on differential equations. So let me just start this part with some like examples, which are very simple, but get some blood into your brain when you think about it. So now even simpler, X is just punctured line. I just remove 0 from the line. So topologically, that space is a circle. The fundamental group is Z, span like generated by the loop around 0, and I call this loop gamma. The first equation is a second order, and I will only be talking about linear equations, like systems of linear equations. So here is this differential equation: Z times the second derivative equals the first derivative. Now, yeah, I should probably hide this and ask you to tell me what the solutions are. Anyway, because I don't have a constant term, this means that the function 1 is a solution. And then you can also check that the logarithm is a solution of this. If the sign is correct. No, the sign is wrong. Okay. Anyway, what happens? So these are solutions near point Z equals 1. This log Z, I pick some branch, right? And pick whatever branch you like, but you already recognize that you have to pick a branch. So there is some indeterminacy, and that indeterminacy is seen by if you want to take these solutions and continue them analytically along a path gamma, the path gamma, right? So if I take the analytic continuation of the constant function, of course it extends to the constant function, so that is not interesting. But what happens to this logarithm is that if I extend it, continue analytically along the path gamma, I get this logarithm plus 2 pi I, well, times f0, which is just 1, okay? So this 2 pi I is again appearing here with relation to some topology. Second equation, now it will be even easier because now it's a first order linear differential equation. Z times the derivative equals lambda times f. So the solution is z equals 1 is v to power lambda, which say x of lambda times log v again pick a branch. And then when I continue along gamma, this one basis vector just gets multiplied by this eigenvalue, e to the 2 pi I lambda. And you see, of course, like if lambda is an integer, then this z to the n is a polynomial, so it's everywhere defined. And of course, there is no indeterminacy. So this e to the 2 pi I lambda is 1. Third equation, and this is the simplest one, but it's the most problematic one for what I'm going to explain. Df over the z equals f. So we have this x of z. And you see, I cannot solve this equation algebraically because this solution x of z is it's not an algebraic function. So this equation doesn't correspond to something in algebra maybe, but it is a global holomorphic solution. I will explain later why this particular equation is problematic and why we want to sort of get rid of it. Okay. Yeah. Any questions about undergraduate differential equations? Okay. So now we get to the maybe more graduate math, which is we give some names to these things that we see, and the name is the monodromy representation. So now again, I mean, of course you could do it more generally, but let's again x be this C with punctures S. So this capital S is alpha 1 through alpha S, and then pick a base point Z0, which is plays the role of this 1 that was on the previous slide. And then I consider a general linear ODE, LF equals 0, L is this differential operator, it's just a polynomial in D over dZ and Z. And well, I allow my coefficients to also be rational functions with poles at the function. Okay? And so then the monodromy representation of this equation is the action of the fundamental group of X with base point Z0 on the space of which I called V of solutions near this point. So at this locally at this point, I pick like the Cauchy here and tells me that I have n linearly independent solutions, which are analytic, and I can continue all of them along the path. Actually, all of them have analytic continuation to the everywhere I want, but it's not unique. And so I get an action of this fundamental group on this V. So I get a representation with values in GL and C after I pick a basis, right? Yeah. So we saw these representations, like here I have 2 by 2 representation where the matrix is lower triangular with 2 pi I under the diagonal. Here I have just 1 by 1 matrix with e to 2 pi I lambda, and here I have a trivial representation. There is no monodromy in the third equation. Okay. Now there's Riemann-Hilbert problem, which is Hilbert's 21st problem. Is basically what I was just saying is whether I can understand the representations of the fundamental group, all of them, through monodromy of differential equations. Okay. And so naive formulation, does every representation come from a differential equation? And actually what we want is, I want to look at, and maybe X is some general smooth algebraic variety, and I want to understand the category, the multitude of all representations, complex representations of the fundamental group, and I want to understand it through the lens of differential equations, okay? And now there is my problematic equation df over dz equals f again. So it has a global solution, which it has, so this means it has trivial monodromy. It gives rise to the trivial representation, but algebraically it doesn't have a solution. So algebraically it's an object. So Now, this naive formulation was whether everything comes from a differential equation, but I want some uniqueness. And now here I have a trivial representation, which comes from the sort of trivial differential equation, but it also comes from this one, and they are not the same. Okay, so there is a solution of this due to Fuchs, which is to consider only look at the singularities of differential equation at the punctures, and I want only to consider those which have what is called regular singularities or Fuchsian singularity. Okay, the next slide I will explain what it means to have Fuchsian singularity, and this is where we start getting slightly technical. But again, I will be talking about actually Fuchs was working in only in dimension 1. This is general enough. X is again C minus some punctures, and I look at this LF equals 0, the differential equation as before. And I take a puncture, but you see here I allow infinity to also be a puncture. Okay, so like my equation df over dz equals f. The problematic one doesn't have any. There are no poles, but it has sort of a singularity at infinity. Okay, so that's the point where I need to zoom in to rule it out. Okay, so there are two conditions that are equivalent. First of them is that if there might not be solutions. So now I pick a puncture, and around it maybe doesn't have any solutions, but maybe I take a sector. Now sector is simply connected, so I will have solutions in a sector. And I look at the growth of the solutions as I near the puncture, and I want that to have moderate growth. Okay, so somehow an analog of being a meromorphic function, except that it has monodromy. And the second condition is a completely algebraic. So the first one is completely analytic. The second condition, which is equivalent, is completely algebraic, and this is what Fuchs discovered. I pick a coordinate t at my puncture alpha. So for example, if alpha is infinity, my coordinate there is 1 over z. And now I rewrite this equation so that it is a polynomial in this t times d over dt. This is what's called the logarithmic derivation. Okay, this one has better properties, and I can rewrite my equation with some new coefficients bi of t with that, and I want these bi to have no poles at the puncture, which is 0 for the coordinate. Okay, so somehow this means that what's called the equation has a logarithmic pole at the point, and then this is the definition. Then I say that the singularity is regular. So examples: log of z and z to the lambda. That's the first two examples I showed you. Have regular singularities. This you can check very easily. But the e to the z equation is irregular because the function e to the z doesn't have moderate growth at infinity, and so we rule it out. Okay. Okay, so here we come to this work of Deligne in the 70s, which is a fundamental contribution to this problem, Hilbert's 21st problem. Now I will give you the baby case first. The general case is a bit more difficult to state. So X is again punctured line, and I have this differential equation as before. And I look at this baby case, so I look at this Deligne's theorem. So I want to understand representations of the fundamental group with complex coefficients. And every representation like that is the monodromy representation of a unique up to equivalence differential equation, which is regular singular. So this regular singularity, this condition of Fuchs, rules out some bad equations and leaves only enough so that we have a bijection between differential equations and representations of the fundamental group. I didn't explain what this is, what this equivalence means, but this is not difficult to explain. Here is the general formulation, like with some words that I will not explain. So X is a smooth complex algebraic variety. So now it's arbitrary dimension. And then we have an equivalence between. First one, instead of saying a differential equation or a system of linear, I mean, of course, you know that a differential equation can be changed. I can change it into a system of order 1 linear differential equations. And then when we want to look at this sort of globally on a manifold and not only locally around the point, then what we arrive at, the correct notion to consider is the category of vector bundles with what's called an integrable connection. So this is sort of an algebraic connection. So E is my vector bundle, omega 1 is algebraic differentials, and I want this to have regular singularities of infinity. As regular singularities, this is a notion that Deligne introduced, which generalizes this condition of Fuchs. Okay, and this is the same as the category of finite dimensional vector spaces over C, endowed with an action of pi 1. Okay.
May I ask a question?
Yes.
And how can we define this equivalence, like in the terms of this probably isomorphism of that vector bundles is integrable connection? This equivalence of differential, is it kind of?
I will explain how to get from this object to that object. Is that what you're asking?
No, I'm asking about this equivalence of differential equations. Yes, and then is it kind of related to isomorphism of integral?
Yeah, it's precisely that. Maybe I explain how to go from this to that. Of course, when I look at this, this is like a system of linear differential equations, and I can consider solutions of that, and they have some monodromy, and I get a representation. It's the same. Okay. Now, this is my promised last slide, when it gets more like I use some more involved terminology, which is ways to go from here from this Deligne theorem, because some of my recent work was related to this. So one is that you can consider equations with singularity. So like my same. Just for intuition, my differential equation comes like this top term, just monic polynomial, right? So d over dz to power n, but it could have some coefficient there, which vanishes at some point, and then gives you a problematic differential equation. And that's also related to topology, and that's this Riemann-Hilbert correspondence due to Kashiwara and Lepkut. That was a fundamental development that relates this to perverse sheaves. Now, irregular singularities, I said we rule them out because they don't correspond to something easy in topology, but they are still interesting to study. There is all this study of the Stokes phenomenon. So that's only in dimension 1. In higher dimensions, it gets extremely difficult, and that's the subject of a lot of development, and a recent work of Kashiwara and Daniolo is one example. What interests me a lot is p-adic versions of this analytic theory. So over the p-adic numbers, we also have some kind of analytic geometry, and then we can study differential equations coming from some problems in number theory and prove theorems in number theory using the theory of differential equations. Here are some names. What I've been working on recently is some non-Archimedean geometry over CW. This is, now I will explain what this is. This is the field of Laurent power series, formal Laurent power series into variable t with complex coefficients. Okay, so this is like a infinite series sum an t to power n, which has only finitely many negative terms, but I don't say anything about the radius of convergence, the formal power series, okay? And over that field, you can do something called non-Archimedean geometry. One thing I wanted to do is to extend these results of Deligne about fundamental groups to this new setting. So I will mention two results. The first one is by my PhD student Felix Rączka, who proved the surprisingly sort of tricky theorem is that what I didn't tell you, that when I have a differential equation, or actually vector bundle with a connection is the correct term, then I can consider it's the Rham cohomology. So I told you about fundamental group cohomology, but then you can combine them and consider the Rham cohomology of a representation of the fundamental group. And so you can construct this, so you can have some Rham complex that corresponds to your equation. And why should the cohomology group be finite dimensional? So this is what Felix proved, that the spaces which maybe not have a direct link to topology are finite dimensional. A theorem I'm working on is a non-Archimedean version of this Deligne's existence theorem. So this correspondence between regular singular differential equations on one hand, and on the other hand, some representations of the fundamental group. In the new setting, both sides of this equivalence are not that easy to define. Okay, so I would say the theorem compares two types of objects, but both of them are rather. Okay, so that's all I wanted to say. Thank you for your attention.
Working.
Can I ask you what does non-Archimedean mean?
Okay, so you have this field. Maybe I would switch on the lights for a second and lay on the board. So you have like my field this. Complex coefficients, and n is bounded from below, right? So that's an example of a non-Archimedean field. Another one is p-adic numbers. And I'm saying it's a non-Archimedean field. What do I mean? I mean that the field has a norm, and the norm has the non-Archimedean property. So what is the norm? So the norm here is norm of some f, maybe this is f, is, I pick some constant, maybe e, to the minus the minimum n, such that an is non-zero. Okay, I look by what power of t it is divisible, and so it is done in such a way that the t to the n goes to 0, right? Okay, so this is what's called the p-adic valuation. In this case, you will have the p-adic valuation. You look at by what power of p the number is divisible, and this has the property that the absolute value of maybe f plus g is at most the maximum of absolute value of f and absolute value of g, right? Right. If two things have a pole of order something, then their sum also have pole of order at most that thing, right? So this means every triangle is isosceles, right? Every triangle is like this. So this is the non-Archimedean field, and it is delicate to work analytically over such fields because everything you think about is highly disconnected. Okay, like the p-adic numbers as a topological space, they are do not contain any connected subsets other than points, right? So, yeah.
I had the impression that non-Archimedean is negation of something, but it's actually
no, it's precisely the negation of the Archimedean property that the integers like. What's the Archimedean property? Is that for every real number there is a integer which is bigger than it, right? And this is related to the negation of that.
Oh, okay.
Right? The integers are bounded in this field. Actually, all of the integers have norm 1, in this case, integers have norm less equal to 1 depending on the divisibility by p, right? So you can, for example, you take the unit ball in such a field, it's a subring. So it's more algebraic in the sense that the unit ball over the complex numbers is not closed under addition, but here it is. So it's a different type of geometry then.
Any other questions?
Can
Okay.
you please again show your theorem about the Deligne correspondence in an Archimedean case? No, exactly this. Yeah.
This is my theorem, and this is the previous slide of Deligne's.
This is in progress means you already know that it really.
I didn't write it down. Yeah,
You didn't know that.
it's not like a. Yeah, I'm stating it as a. I put it here as a theorem. Yes.
Okay.
Yeah, well, I have two related questions. Firstly, can you tell from the equations from a ring whether the algebraic right is simply connected? You know, we know that there are different fundamentals.
So now you're asking.
And the question, which is vaguely related, is what about, you know, applying some rational homotopy theory? So can you discover the minimal modeling? You had the theorem that the Rham cohomology is isomorphic, it's algebraic around. So it's a natural question to ask whether you can discover minimal model in the sense of rational homotopy.
Okay, so answer to the first question, I think it's a delicate problem. So you're asking to say, for example, there, in principle, there could be a group which doesn't have any finite quotient, right? So it has trivial pro-finite completion, and also which doesn't have any complex representations of finite dimension either, right? Maybe such examples are known. Maybe Piotr would know better than me. And now we ask whether that group maybe is a fundamental group of an algebraic variety. And I think I think it's open, this problem. About rational homotopy theory, I don't know. I know that the people are interested in rational homotopy of algebraic variety, but I personally cannot say.
Okay, thank you. Thank you, Ron. Nie wiem, czy nie zrobili tego ten. Przerwy sterowane.
Nie wiem. Nie wyłączałem czerowania. Tak jest, wyłącznie czerowanie.
Okej, dobrze. Tak,